Welcome, everybody. Thanks for coming. Some of you already heard about MySQL and Kubernetes and operators, so I'm going to talk a little bit about PostgreSQL and Kubernetes and operators. One of the people I want to actually call out to begin with is a lot of this is the work of the engineering team at Zalando, a major European retailer. And so a lot of the stuff that you're going to see was actually written by them. What we're going to be going over here is the basics of how to deploy PostgreSQL and Kubernetes in a simple way to get you up and running right away. And then you can go beyond that on your own. There's a lot of documentation out there. There's a lot of plugins and a lot of different options. We're not going to actually have time during this session to show you all of them. Rather, I'm giving you sort of an orientation and a demo of the basics. I'm going to assume that you have some basic knowledge of what Postgres is and how you interface with it, what Kubernetes and or Docker are and how you interface with them. If that isn't, you just sort of coast along and hopefully the demo will clarify things for you. So we're going to go over a few things. I'm going to do some talking, first of all, to explain what problem it is that we are solving with this, why we would want to do this in the first place. And then I'm going to do a bunch of demos to show you how we're going to do this. So all of this is off of my PG Kubernetes tutorial, which is up on GitHub. You can use that as a self-paced tutorial. Download Minikube, run it yourself. I will actually be pushing some updates to that later this month because currently it runs against older versions of a lot of the software, but it does work and it does give you the experience. So let's talk a little bit about why you would want to run Postgres, or for that matter, any other database on Kubernetes in the first place. So the big thing is that, first of all, people say, when they're talking to me about maybe, oh, hey, it's sort of interested, we've got this Kubernetes thing, it's great for the stateless stuff, how do I run databases on it? And what they're often asking is, how do I run my ginormous central business database that's got 16 terabytes of data and 50 applications connected to it on Kubernetes? And my answer to that is you probably don't. There's not any advantages to running that database in a Kubernetes environment, except under special circumstances, and there's a lot of extra steps. What Kubernetes is there for is all of the little databases. A few years back, Peter Van Hering of Heroku came to speak at a Postgres conference. He said, we've got however many they had at the time, 500,000 Postgres databases in our environment, and 98% of them are less than a gigabyte in size. So those are the databases where you have a really big win in moving them to a container cloud environment and moving them to Kubernetes, because these are small databases, they support one application, they're usually not that critical, which means you really should not be thinking about them at all. And the automation that I'm going to show you is a way to not think about them at all. So think of this in terms of how do we run lots of little databases, not how do we run that one ginormous database. Now, there are a few options in the environment, which is the Postgres community we're talking about here. And the Postgres community never does things only one way. So like the two major ones I'm going to be talking about, most of this presentation is about Patroni and Spilo, which is the stack that I work on for hosting this. There is another one done by Crunchy Data Corporation, their Crunchy PostgreSQL Operator. That one was created by Crunchy Data. It's a very enterprisey solution. They are actually looking more at that, how do you manage that one big database. It's officially supported on OpenShift and OpenShift.io as Red Hat partners. By the way, I work for Red Hat, if that wasn't clear. I work for Red Hat, so they are Red Hat partners, and so they've got enterprise support with an SLA operating in that environment. Now, the Crunchy operator is very much focused on the more enterprise use case. So it's fairly complex. It involves, I think, 14 different container images. So one's for databases, one for proxies, one for monitoring, one for backup, another one for other maintenance stuff and that sort of thing. So there's a whole bunch of different container images, which makes it sort of conceptually complex. I personally prefer a much simpler approach, as do some other folks. So let's talk about the use cases for the simpler approach. And the first one we're going to start with is Zalando because they have been the technical mainstays of this project. So Zalando.com, they're the top fashion retailer in Europe. They actually outsell Amazon and its possessions in terms of clothing ordered online in Europe. They have an entirely AWS-based cloud that they run. And they have a very strong DevOps orientation, which means they want most things to be self-service for their development teams and autonomous. And because they're doing this, this means that they actually have hundreds of databases, one per application, one or more than one per team. So as a result, this is the sort of environment they want to enable. They want to enable getting the DBA out of the way in terms of database deployment, database maintenance, everything else. Second one that I just got off of implementing here, for the Cloud Native Computing Foundation, which is the nonprofit that backs Kubernetes, along with a whole bunch of other technologies, but most of them associated with Kubernetes, and for the Linux Foundation in general, we have a community metrics system called DevStats that keeps track of who your contributors are and what they're contributing and who comes and who leaves and how much they're commenting on things and whether or not PRs are held up and all kinds of other things that you're interested in with a contributor community. For DevStats, we had some design goals. We wanted to actually be able to move it around because the Linux Foundation uses a lot of donated hardware and cloud time. And so when those donations run out, we move things. So we wanted to be able to move it from AWS and GCE, move it to bare metal if we wanted to. Needs to be HA because there is a full-time technical support staff of one. And because the database is entirely embedded within this data analytics application, the crunchy solution was actually too complex for that environment. It has a lot of extra stuff that's not optional and that they don't actually need because the database needs are very simple and easily contained. So for both of these, we adopt what I regard as the 80% solution. That is small databases, not necessarily small in size, but at least conceptually small, databases that support one application, fully automated high availability, HA that's oriented towards availability first, and this is your basic sort of decision, availability first versus consistency first, et cetera. CAP theorem, you have to make decisions. Relying on Kubernetes itself for things like load balancing. And initially, and usually a big concern for people is it being friendly to the AWS environment. There's a lot of people running in the AWS environment. And these are the things that Patroni fulfills. Now, I've mentioned the name Patroni a couple of times. Let's actually look at what we're looking at when we're talking about Patroni. Oops, why is my caps lock on? Because there's a cable here. I don't have a Docker file there. So one of the approaches that we took in order to keep Patroni as simple as possible is a sort of golden image approach. So there's basically two approaches you can take when you're developing a Kubernetes microservices for something, right? You can say, I'm going to have a container image for every function that I'm going to do, right? So I'll have one image for backups, one image for shelling in, one image for monitoring, one image for something else. And that has the advantage of having minimal image sizes and very specific images that you only rev when their exact dependencies change. The problem with that is it's a lot of mental burden. And so within the Patroni project, we took an opposite approach, which is we said we're going to have a container image that contains all of the tools that you need to run Patroni in whatever context it is. And this is that image, which actually goes through, it's based on the upstream official Postgres image on Docker Hub. And then we add a few things to it. And the important thing is that we have this entry point. And the entry point creates a configuration file and then calls this application called Patroni. And the Patroni is a Python application that manages Postgres. Now, I've thrown around a couple of words here. You're going to see two appearing in this demo here. Patroni is this high availability daemon written in Python. It was originally based on some code released by Compose.io before they were acquired by IBM. Theirs was sort of a proof of concept. I and the Zalando folks picked it up, turned it into a production application. By the way, all these slides are online with the PG Kubernetes tutorial, so you don't necessarily need to take pictures, just saying. Now, the Zalando folks also use another name that comes up in the realm of the operator, which is Spilo. And Spilo is this golden image that contains everything, Patroni, Postgres, and a whole bunch of utilities. You can use Patroni without Spilo, and I'll be demonstrating that. You can use it with Spilo, be demonstrating that as well. Now, so this Python daemon, what this does is it controls PostgreSQL start, stop, and replication setup. It automates failover, and it supplies a management API for the Postgres running inside that container and for the cluster as a whole. The idea here is that within each container, you have this pilot. This Patroni is Italian for governor, this governor, and then you have Postgres. And so when you start up the container, one of the ideas of containers is that you have a PID1, you have an executable that the container starts. The executable in that case is not Postgres. The executable is actually Patroni, which starts Postgres as a child of it. And this is critically important because we want to make sure that if the individual Postgres node loses communication with the overall cluster, Postgres stops running. Because if it doesn't, then you can have split brain, which is bad. So let's actually look at what that's like to set up. So I actually have Minikube running on this machine. Minikube's a demo testing thing for Kubernetes. I wanted to show this on our storage testing cluster, but it was being a little iffy with the Wi-Fi, and so I decided it was better to do it locally. So the way that you deploy this is, oh, why is it? Okay, hold on. Okay. The way that you actually deploy this is as a set of Kubernetes objects. Now in the demo file, we've actually just sort of broken out all of the objects into the different sections. So one of the things that you want to think about with a Postgres cluster is you have read connections that can be load balanced to all the nodes, and you have write connections that need to go to the master. The other thing that we do when we create this on Kubernetes, we create it as a stateful set, which is designed for stateful services like databases. And a stateful set actually requires an attached service. Now, this is actually convenient for us because it works well for that attached service to also be the load balancer for the read connections. Now, in this case, we're using built-in Kubernetes round-robin load balancing. This is really very simple-minded. It's like on new connection, round-robin load balance the connections. Turns out to be good enough for most small applications. If you need something more sophisticated, then you would actually look at Istio or putting PG Bouncer into the mix or whatever. And so we create that load balancing connection. We actually do something that you will almost never see anywhere else in the world of Kubernetes, which is manually create an endpoint. Usually in Kubernetes, endpoints are implicitly created as part of a service. A service in Kubernetes is, here's this network resource that you can connect to that does X, right? And these create an endpoint that actually attaches to an internal IP address so that you can connect to a pod. And normally this is all handled implicitly under the hood by Kubernetes, but we actually need to create one manually because we use the location of that endpoint to determine who is the master. Because within the Kubernetes cluster, one and only one pod can own that endpoint at any given time. And therefore, by controlling where the endpoint is, we can make sure that we don't end up with split brain, and Patroni controls that. Now, then we create a separate service that points only to the master related to that endpoint. Now, from there, we're going to create a stateful set, which is, again, how Kubernetes to stateful applications. There's a lot of stuff in here, what service is attached to, a bunch of information for this. We create actually two ports for the container. One is the Postgres port, the other one is a management port for that management API for things that you can't do through the Postgres port. Have to have a volume, obviously, or we can't store data long term. And then you can pass along a whole bunch of environment variables using Kubernetes config maps or otherwise in order to control the behavior of Patroni and Postgres itself. There is an extensive documentation on Patroni read the docs about all of the variables that are available. There's like, I don't know, 80 or 90 of them. I'm not going to go over them here. Some of the basics we need to set up is, passwords for the super user, what ports we're listening on, which by default is all of them, and that sort of thing. And then allocate some storage. You're going to want to create some secrets, which include, passwords for things. And then the other thing that we actually need to do is, and this gives people some trepidation, we need to get into Kubernetes RBAC because the Patroni daemon that's running inside a container needs to be allowed to change certain things about the Kubernetes cluster. Mainly, it needs to be able to change the service and the endpoint so we can redirect connections to the current master, which by default, a process running inside a Kubernetes pod cannot do, which is a good default, but we need to open it up, and that's what this RBAC template does, is that it goes ahead and says, yes, containers of this type are allowed to change services of this type. See if we can catch that. So what's going to happen is it's going to actually spin up one pod at a time, running Patroni plus Postgres. And as the pods spin up, they try to have a master election. Now, because of the way stateful sets work, your initial master is always going to be node 0, because node 0 always gets spun up first. And then any other nodes will start replication from that master. And you can see here, we get some log action from here that from Patroni's own output that basically says we have the leader, and then this is a follower, and it's telling me who its leader is. So that's all the things that we created, and that's kind of your minimal thing. And it's always useful to understand this, even if you're using an operator or something. Because if you decide you want to modify the operator, if you have to troubleshoot something, you want to know what it's doing. So again, what happened there is actually we're running Postgres in a container with the Patroni pilot. Kubernetes spins up any number of nodes according to our stateful set. after the nodes are spun up, the Patroni daemons running in the individual containers have a leader election. And they use the Kubernetes API to do this. So they call the Kubernetes API, which calls etcd, which then has a contest for who gets a lock over the resource, and whoever wins that contest becomes the master. And then the other nodes are told that they are replicas, and they start up replication from whoever the current master is. Now, one of the reasons why are we doing all this? One of the reasons we're doing all this is that we want high availability and automated failover. That's obviously, hold on, I'm out of order here. That is obviously the critical part of all of this, or it's not worth doing. So let's talk about how failover works, right? So something happens, we lose a master, right? We shut down that AWS instance, the machine fails, we run out of resources in that node, and Kubernetes auto-migrates stuff to a less overfilled node, whatever. We lose a Postgres. So then what's going to happen is the replicas have been checking constantly whether or not there is a current master. And when that check fails, the replicas contact the Kubernetes API and they say, we need to hold another leader election. And then they hold, actually at this point, a two-stage leader election, one which checks who gets the lock on the new master resource, and the second checks who is where in terms of replication, because we don't want to fail over to a replica that for some reason, like say being off the network for a while, was not caught up in terms of replication. Then one of those wins that leader election, and we start replication to the existing nodes. At that point, Kubernetes is going to, because it knows it's supposed to have X number of nodes in the stateful set, it is going to deploy a replacement node, which will immediately fall into the replica role. There are some other peculiarities to this, because like, for example, if the replacement gets started up where the old master used to be, then it is going to have differences in its transaction log that are not reconcilable. Depending on your Patroni settings, it will actually roll back and in order to join the cluster, or it won't, so that you can manually recover any data that you might have lost in network communication. So let's actually do that. So we've got our pods here. Now, I don't, because I'm running on Minikube, I don't have the ability to actually physically kill off the node. So instead, we're just going to delete the pod. Oh. Okay. Okay, that was, it's not quite that fast when you're actually running over a network, obviously, because it takes a little bit longer for everything to communicate with it. But if you actually look at what happens here is we lose our connection to the master. At this point, the replica checks with the Kubernetes API to say, hey, should there be a master here? It then has the leader election. It wins the leader election here. Says it's the leader. You've got some other stuff going in the background with the replication slots when the other replica is connecting to it and establishing a replication connection. So it all happens automatically.
So Josh, what happens to the data set then? So for example, if you had high transaction,
yes.
Right?
This is configured with asynchronous replication. Right. So like any asynchronous replication failover, you are possibly going to lose a few transactions. Right. So then, and that's why there is a setting in Patroni called use PG rewind to decide whether if the old master recovers, whether it should erase those transactions so that it can rejoin the cluster, or whether it should just hold. for manual recovery. Because those are your two choices.
Node automatically, right? So you've got that additional
Yes.
node that was,
Right.
say, X'd out, right?
Yeah.
And then you're supposed to manually recover that data, right? From that node.
Well, the thing is, so one of the things that's different about stateful sets in Kubernetes is that Kubernetes tries to hold on to your stored data, which are called persistent volumes, right? So we only lose the persistent volume if we lose the physical storage. Kubernetes will not erase those even if you manually delete the stateful set. That means that if Kubernetes assigns a replacement node, and that replacement node can still access the same storage, it will actually recover that database. Whether or not it's a good thing depends on what you were expecting, right? Most of the time it's a good thing. But if in the meantime we failed over masters, it's possible that Patroni demo 0 could have a transaction that Patroni demo 2 does not have. And then at that point we have to decide what to do, right? Is it our priority to have 3 nodes available at all times? Or is it our priority to never lose a transaction? And that is, any transactional database, when you're talking about failover, those are your trade-offs, right? Is to say, is consistency more important or is availability more important? And you always have to decide on that. And that's up to you. And you can turn that setting off, in which case Patroni demo 0 would attach the same storage, but then it would not become available. And it would not become open for connections because it would be waiting for an administrator to intervene in order to recover the lost transactions.
So if we lost some transaction, can we manually synchronize them?
Not if the new master has accepted write transactions. At that point, you have what are called divergent timelines. So the only way to reconcile it would be to literally hand reconcile it on an SQL level. Because this is Postgres replication we're talking about, which is binary replication. It's all page level diffs. And there's no way to reconcile those on an automated basis. Or even, there's no way to reconcile those on a binary basis. You'd have to reconcile those by rerunning the same SQL transactions. So that is our failover. Now, all of this has been a manual Kubernetes deploy, which frankly, let me say, is good enough for a lot of people. Like for the DevStats deployment, we just created a Helm chart. Helm is a deployment tool for Kubernetes, so we created a Helm chart and deployed on that basis. We did not use an operator because on there we have 3, maybe 4 Postgres instances on their cluster. And so there just did not seem to be a need to actually go the operator route with that. However, if you have more databases than that, or if you have a lot more of a CI/CD process going on than we have in DevStats, then you might want to actually look at a more sophisticated approach. Now, the idea of operators is these are small programs that run in your Kubernetes cluster that actually manage specific services with complex needs for you. If you go on Operator Hub, you'll notice that most of those operators relate to databases because that is the first thing that comes to everybody's mind as a complicated service that needs special software to run it. There are some advantages to the operator approach, which is you can take a much more declarative approach towards creating, maintaining, modifying Postgres clusters than is necessarily easy to do with Kubernetes YAML stored or Helm chart stored in a GitHub archive. Also, with operators, it's easy to add things in like scheduled cron jobs and other dependencies that are not in the form of just a pod and a service running than it is by manual deployment. The other thing is that, hey, we're going to be dealing with a lot of YAML manifests anyway. It would be nice to just have one manifest that controlled everything. And the operator approach enables that. So I'm going to show you Zalando's operator, the Spilo operator, because that's the one that they worked on. It's continually updated. This is the operator with some extra tweaks that they actually do behind the scenes, but it is the core of the operator that they run in production. And it's a good one for you to actually look at. Now you have to do a few things to create the operator. I need to create a config map. Config maps are how Kubernetes stores configuration information, unsurprisingly. And I need configuration information for the operator itself. Again, we're back to RBAC. RBAC in Kubernetes is mandatory, as it should be, because otherwise you're running completely insecure. And so I have to give the operator permission to do things, or it doesn't have any permission to do things. And then I create the operator itself. Okay, and so this creates what's in Kubernetes lingo a CRD, custom resource. I always forget what the D stands for. Anyway, definition, custom resource definition. And CRD is actually Kubernetes extension, as in this is a completely brand new type of object that you can create and then add to Kubernetes with its own properties. And this is how operators are handled, is that they are all CRDs. And so we've got this PostgreSQL CRD now that has its own properties. And then we actually go to manifest, right? At this point, we've deployed the operator, but we haven't actually deployed any Postgres at all. Because the idea is that the operator is a program that controls multiple Postgres clusters. And so we now have to give the operator a definition for each cluster we want to deploy. And so this is a definition for a sample cluster. And I said you'd see the Spilo name all over the place. And so this uses the Spilo golden image, which is Patroni plus a whole bunch of other stuff, plus backup, plus management stuff, plus proxying, plus a bunch of other things. And you tell it what you want to deploy, right? So we're going to deploy PostgreSQL version 10. We're going to have a database on there named Zalando. There will be a user named Zalando that will have certain permissions, et cetera. And the idea is that doing this kind of deployment to the operator is part of your CI/CD workflow, right? You do this in dev for the dev environment, you do it in staging for the staging environment, and then in the production environment you have the same sort of manifest. And the nice thing is that aside from the location of the cluster, the manifest can actually be the same in each environment, making it easy to do CI/CD. Okay. There we go. Hopefully this will. Okay, I'm actually going to shrink this a little bit, just because I want to actually be able to see. There we go. So what's going to happen is that the operator is going to create a new cluster. And then after it's done creating the new cluster, it's going to assign one master. Now this works with Patroni under the hood. It's the same way. The labeling is a little bit different, but it's the same underlying technology. So now, I've showed you deploying and failing over clusters. But of course, a database cluster is only useful if you can actually connect applications to it. And this is actually where running in the Kubernetes environment and running with operators or deployments HA makes things a lot simpler, because you don't have to store credentials in any of the application code. You don't have to store, for that matter, any information about where the current master of the production database setup is there. You just use the fake DNS names supplied by Kubernetes and whatever secrets you've set up in your Kubernetes environment in order to supply all that information to the application. So the application code doesn't have to change if you move the database around, which is really nice. For example, I'm going to be using Kubernetes secrets in order to get passwords. Now, Kubernetes comes in with a really simple secrets mechanism that just hashes everything. It's not very robust in terms of actual security. If you're concerned about that, there are a number of Kubernetes plugins like HashiCorp Vault that supply a much more robust level of security. Or Keycloak, which is my employer's version that we use with OpenShift, that supply a much more robust level of security, but your interface to them is still the Kubernetes secrets mechanism. So, now I'm actually going to create a Postgres client pod here, which I need to do because by default, Postgres connections are only available from within the Kubernetes cluster, right? In order to make Postgres available to the world, I would have to actually publish the interface, which you don't normally do, right? You don't normally publish your database applications to the world. See, is that up and running? There we go. Ooh. Okay, that's not good. Okay. So, some live troubleshooting here. I'm actually going to switch to an image I already have cached and see if that works better. Okay. Okay, so that'll take just a minute. And okay, I don't know what's going on there. I seem to have lost my ability to connect to Docker Hub. And it's not using, whoa. Okay, I'm gonna have to skip that demo. So I'm gonna have to see whether or not I can do the next thing either. So now the idea of part of this is in order to be able to have a full sort of DevOps workflow, including the databases. So an idea of this is you'd use operators or deployments, create your own customized version of the containers, create your own manifests, create a workflow for deployment. Now, none of this addresses the contents of the database. That is a completely separate part of your workflow, hopefully controlled by the application. How a lot of this is actually handled is on two levels. One is Patroni is given an initial configuration that controls a lot of stuff about how Postgres runs, various security settings, memory settings, and that sort of thing. For management, I recommend that you limit anything. Patroni can set any configuration variable that Postgres has. But I actually recommend that you limit the initial settings to things that have to be set at startup time, because you can use the management API in order to set things after Postgres has started. So let's actually do that. Oh, yes, I do. Thank you. Okay, So I'm actually, I'm doing this by just execing into one of the running pods because of that. And so now the management API is a REST API. That just gives us some JSON output on what's going on with Patroni, including what version of Patroni are we using, where we are in the replication stream because of the replication management system, a bunch of other things. You can actually use this to monitor replication progress if you care to. But what you really want to do is manipulating the JSON, though possible is annoying. So instead, we created a client called Patroni CTL that calls out to this API and interprets the output. This shouldn't be an internet issue. This is running locally, so I'm not really sure what's going on. KVM is having issues. Ooh, okay. Okay, well, we're going to wait for that and hope that it comes back. Right now it's crashed. We'll see if it actually comes back. So, from API management, that sort of thing. So, stuff that we're working on in the future, Postgres 12 support will take a little while because for Postgres 12, we've merged the replication configuration with the main configuration file, but that requires making some modifications to how Patroni works in order to continue to allow people to make changes to their base configuration without clobbering Patroni. I'd like to get in there better statutory support for synchronous replication. Right now, you can do synchronous replication with Patroni, but it's kind of out of band, and Patroni doesn't really do a good job of managing it for you. And I think we could do better. Better cascading support for multi-data center installations. Right now, the way that you do that is you establish a Patroni cluster as a special kind of follower cluster, and then point that to the main data center as its lead. Again, I think we could make that a little bit simpler. Support for Postgres logical level replication. We need to actually, we would only be the simplest version of that, which is you're replicating an entire database because we can't manage choosing and picking tables to replicate, not to replicate. And then, of course, as always, expand the documentation. Our documentation is pretty good right now, but there's a lot of things it doesn't cover. Other dev that we're working on, I'm personally working on a new non-Spilo operator because I want to put an operator in Operator Hub. And the Zalando guys just don't have any interest in Operator Hub. They don't care. Plus, I want to have a smaller image than the Spilo image, which contains a lot of tooling that Zalando needs, but most other people don't. Also look at integrated load balancing using something like IPVS or Istio in terms of having more sophisticated load balancing. And the reason why looking at logical replication support is that would give us automated upgrade support. Because the way that you upgrade Postgres now is you start logical replication to a new cluster, running the new version. When that logical replication catches up, then you fail over to the new cluster. Something I think that Patroni could automate in the future. And then, of course, I would like to see more of the companies, the Postgres ecosystem, offering official support for a Patroni-based deployment. Because I work for Red Hat. Red Hat does not offer support for databases directly. We do it through partners, and therefore I want to have more partners available for this. So overall, public project, completely open project. It may be under Zalando, but we accept PRs from everybody. We have a Slack channel in the Postgres Slack. You can also discuss Patroni under SIG apps in Kubernetes. But if you're interested in this, if you're interested in deploying it, if you discover it doesn't have features that you need, it's Python code, you can probably figure it out, submit a PR. This is a whole list of other resources here. Look at documentation and everything else. Here's the main resources for a lot of things, including the crunchy data operator. So let's see if we came back. Yes, we did. There we go. Okay, so I'm going to go through the interface here. So Patroni demo list is just going to show you who the list is. This is going to show you any non-default configuration options. Remember I said the use PG rewind. That's our setting for discard transactions if you need it to rejoin the cluster. And so one of the reasons we have Patroni CTL there is sometimes failovers aren't expected, right? You lose a node. Sometimes failovers are expected, right? I am, repaving this particular server, and therefore I want to fail over to a Postgres node that's not on that server. Or I'm gradually upgrading the Postgres version in all of the containers, and I want to fail over. And for that reason, we actually have manual failover commands. Such as switchover, where I'm prompted to choose a new master, just accept the defaults there. And a switchover does a clean failover, as in it halts one of the nodes, pushes all the transactions out, does a clean failover. There's also a Patroni control failover command to do an emergency failover. When, say, for example, the current master is not responding, but for some reason automated failover is not kicking in. Okay, so that's all I'm going to show you for the demos, unless people have particular questions. So we'll give about 5 minutes to take, or 3 or 4 minutes to take questions from people. So more questions.
For the application connection, right?
Mm-hmm.
You mentioned that you publish or Patroni publishes one specific URL, right? One specific DNS.
Well, 2 of them actually.
Okay. Can you go just a little bit deeper into how application
Actually, hold on.
switching the nodes or actually changing the machines altogether, right? Let's say
Yeah.
you have to move by some data center disaster. How would you have your application connecting to the same URL?
Well, I guess the question is, where's the application running at that point? Because the question is, do we have failover from data centers, right? Right, and it really depends, right? If the application is running in the new data center, then you just set up the new data center with the same internal discovery addresses as the old data center, and then nothing changes, right? Because those discovery addresses, those DNS addresses are local to the Kubernetes cluster. However, if the application might be running somewhere else, then you're going to need a more complicated approach. And the question there is going to be, how do I redefine the discovery within a sort of federated environment? And that's kind of a work in progress in Kubernetes. Yeah, I mean, like the quick and dirty way to do it would be, Patroni has this thing called service catalog. Now, normally service catalog is used to connect to services that are not Patroni. Kubernetes has this thing called service catalog. It's normally used to connect to things that are not part of Kubernetes, like an external service like RDS or something like that. But you can actually use it to connect to anything. So you could very well publish the Postgres port outside of the cluster in the new location, and then use a service catalog wherever the application is located to point to that, if it's on a different cluster. I mean, for that matter, if they were on separate Kubernetes clusters, you'd be doing something like that anyway. So all you need to do then is redefine the service catalog. More questions? And
the weirdness of the endpoint that's created so that it can handle the election between the nodes and whatnot.
Yeah.
Is there a future where the operator takes a more direct role in that process?
Well, I mean, if you're doing the operator, it's creating the endpoints and that sort of thing. We looked at using, because there's been some code published for locks within an operator, for like operator-based locks, et cetera. But the thing is that code is actually kind of complicated and doesn't avoid the race condition we're avoiding with endpoints. Because the advantage of the endpoint is it's atomic, and it also controls where new connections get to connect to. And so by changing the endpoint, we change who's the leader and who owns the leader connections in one action. Whereas if the lock is located anywhere else, then it's two actions. And there's the possibility that we could lose the current master between those two actions, at which point you would go through a period of incoherency before things settled out. And during that period of incoherency, you could actually have two masters accepting rights. So I don't see getting away from endpoints for that reason. Where we would get away from endpoints is for anybody using an optional integrated load balancer approach, right? If we're using something like IPVS or whatever to manage the Postgres connections, then we would control things there. Let's see if I can actually do this from the node. And the answer there is no. Oh wait, PG Shell is running now. So let's hop into PG Shell and I can actually show you that. Oh. Wrong kind of hyphen. So Patroni demo right here is my master connection. So this is the completely confusingly named call that we use to say whether or not something is a replica. It has historical basis. And so if it's false, then we are a standalone or a master and not a replica. So that was our master connection. Now, if we want to load balance, then we use the other service, the one that load balances. And actually, on first try, we got a replica. Now, it load balances among all nodes, so a third of the time we're going to get the master. Because again, super simple-minded load balancing. But that way you can actually have two different connections with two different service names that you're using, one for reads and one for writes. That's how we have a devstat setup, right? Is that we have the cron job that actually writes to the database by digesting all the information from GitHub and elsewhere, and that uses the master connection, and then the Grafana applications that display all of the graphs use the load balancing connection. Okay, so I got to do all the demos. Any other questions?
What are your experiences with the limits of where you, basically the quantity of applications, and let's say the applications are a quarter writes, 3/4 read, just for example, where do you hit sort of your need where you have too many applications coming into the front end, the front end to the cluster?
You mean too many to run it on Kubernetes, or?
Yes, to run it in
Yeah.
Kubernetes.
So,
I think of the right words.
yeah, it's so the question of sort of sophistication, and the thing is, there's no firm line there. It's just a question of the more centralized your database is, the less advantages there are to running in Kubernetes, and the more potential disadvantages, right? So like at one end of things here, we have a small database that is attached to one and only one application, and is on that application CI/CD cycle in terms of development of the database structure code itself, et cetera. That is the perfect case for host this on Kubernetes. There's lots of advantages, not very many disadvantages, right? And then on the other end of things, you have, this is my 16 terabyte database with 10 years of transactions, and we have 40 different applications communicating with this, some of which are third-party vendor applications that we don't control. And that is a very bad case for hosting it on Kubernetes, Like I would try several other things before I went to, oh, let's put this on Kubernetes. And anywhere in between there is going to be a judgment call, right? Because part of it's going to be other environmental questions like, how devoted is my development staff to Kubernetes, right? Are they Kubernetes enthusiasts or are they using it because management said that they should? How, is our sysadmin staff, how comfortable are they with it? Are we using a public cloud hosting where we're planning on moving everything to, say, GKE, and we need to host it on Kubernetes for that reason? Like all kinds of other things, right? You're making a trade-off cost decision. And you just have to kind of add up the factors in there and make a decision on what makes sense. For people with large environments with lots of databases, what's going to happen most of the time with this is the old databases are going to stay on bare metal. And it's the new databases that are created as single application databases that are created under a more DevOpsy model that will actually end up getting hosted on Kubernetes.
Thanks.
Welcome. Anything else?
Have you experimented or tried tying this into any type of pod autoscalers?
I have not experimented with pod autoscalers. We actually have an outstanding bug under Kubernetes with help wanted on it, where we're not giving the right kind of resource information for the HPA. So we'd need to fix that first.
Is there any OS recommendations? Is it like always Red Hat or CentOS?
Well, yeah, for me, yes, because where do I work, right? So,
Is there a typo on the screen in the middle where it says Debian?
that's because the container image.
Okay.
Yeah, that's the other reason why I need to build a new operator and stuff, because I need to actually do a Patroni image that's based on the UBI. So back when Docker Hub was first launched, I was mainly using Ubuntu for stuff. This is like 8 years ago, something like that. When was Docker Hub launched? Actually, it wasn't that long ago, 2013, right? Anyway, so when Docker Hub was launched, I was using Ubuntu for most things on the server, and so, and there were also issues with yum.postgresql.org at the time. And so when we created the canonical Postgres image on Docker Hub, it was based on Debian. And the Patroni image that we have here wraps, it's a layer on top of the canonical Postgres image so that it's easy for us to keep it up to date, right? We just rebuild it and we get whatever's the current Postgres image. If I do a new one based on UBI, which obviously my employer, UBI, by the way, is the Red Hat container image that can be either CentOS or Red Hat Enterprise Linux, depending on your licensing situation, that we released recently. And if I do one based on UBI, then I become responsible for keeping Postgres up to date and not just Patroni. And so that's why I haven't done it yet.
Makes sense.
Okay, well, thanks, everybody.